The AI race is usually framed as a contest over the biggest models, the fastest chips, and the largest data centers. But the real pressure points are often much quieter. They sit inside the light source of a lithography machine, in the tool portfolio of a Chinese fab supplier, in the substrate behind an optical device, in the routing logic of a language model, in a city registry that determines whether AI services can launch, and in a European rulebook that can shape market access far beyond Europe itself. Taken together, these are not side stories. They are a map of the bottlenecks now shaping how AI capacity is built, deployed, and sold. Start with the hardest physical constraint in the semiconductor stack: extreme ultraviolet lithography. ASML still dominates the machines used to print the most advanced transistor patterns, which makes any credible attempt to improve a core EUV subsystem worth watching. That is why xLight has drawn attention. Chaired by former Intel CEO Pat Gelsinger, the company is reportedly developing a free-electron laser light source that could serve as an upgrade path for existing EUV systems. The reported claims are ambitious: a 30 to 40% improvement in wafer processing efficiency, and wavelengths as short as 2 nanometers. Those claims should be treated carefully. Based on the available material, there is no confirmed partnership with ASML, no disclosed customer commitment, no timeline, and no independent validation. So this is not yet evidence of a breakthrough. What it does suggest is something more basic, but still important. Even in the most concentrated corner of semiconductor manufacturing, the industry keeps searching for incremental gains inside the most difficult subsystem layers. That matters because even a modest improvement in light source performance can affect tool productivity, fab economics, and eventually the amount of leading-edge chip capacity the industry can bring online. If xLight points to the ceiling of advanced lithography, AMEC points to the floor. China is trying to build underneath its own semiconductor manufacturing base. The company has reportedly developed 54 types of high-end semiconductor equipment, including categories such as plasma etching and thin film deposition, and it is targeting more than 100 tool types within 5 years. That does not mean it has closed the gap with global equipment leaders. The available material does not confirm named customer deployments, fab-level qualification, or sustained production milestones. Still, the strategic logic is clear. In an environment where access to foreign tools can be restricted, domestic breadth becomes a form of resilience. Process tools shape yield, reliability, and continuity of production. So a push to cover more categories rather than perfect only a narrow subset reflects an industrial strategy aimed at reducing external dependency across the manufacturing chain. The key question is not whether AMEC can expand its catalog. It is whether that catalog can be translated into equipment that fabs are prepared to trust in high-volume production over time. That distinction matters because in semiconductors, capability on paper and capability in a live fab are not the same thing. Materials form another layer of the same manufacturing story. That is where the agreement between AXT and Lumentum becomes relevant. AXT has signed a definitive long-term supply agreement to provide indium phosphide wafer substrates to Lumentum operations through 2031, supported by 2 deposits of $43.5 million each from Lumentum. Indium phosphide is not a mainstream material. It is used in photonic devices tied to high-speed optical transmission, part of the infrastructure that supports data-heavy networks. The structure of the agreement is what stands out most. A customer paying capital upfront to secure multi-year supply signals long-range planning. It does not, by itself, prove an active shortage. It does, however, show that upstream materials are becoming important enough to justify deeper contractual commitment. The regional aspect needs care. The source material references both the United States and China as relevant regions, but it does not specify where production takes place or confirm China-linked manufacturing under this contract. Even with that limitation, the broader message is visible. Materials once treated as secondary inputs are becoming part of strategic supply planning, especially where optical infrastructure is concerned. From manufacturing inputs, the story moves to what happens when hardware itself becomes a constraint on AI development. That is the context for Alibaba's Qwen3.8, described as the company's largest foundation model so far, with 2.4 trillion total parameters. But the more important point is not the headline size. It is the architecture. Qwen3.8 uses a mixture of experts' design that activates only about 95 billion parameters during a given inference task, instead of running the full model each time. In practical terms, that means a user query is routed to the most relevant subset of the model, rather than the entire network. The result is lower computational cost and reduced latency. Strategically, that efficiency matters. If access to leading-edge accelerators is tighter, then competing only through brute force scale becomes more difficult. Architecture, routing efficiency, and cheaper inference become alternative ways to stay competitive. The model's reported focus on professional office tasks and coding also suggests a deliberate orientation toward enterprise-relevant workloads, rather than general-purpose showmanship. What the available material does not support is any firm ranking against global rivals. There's no independent benchmark evidence, no detailed training stack disclosure, and no adoption data. So the significance of Qwen3.8 is not that it has clearly surpassed anyone else. It is that it reflects a visible adaptation strategy. If hardware is constrained, software efficiency becomes more valuable. Even the best model means little without a route to market, and that route increasingly runs through administrative approval. Shanghai's Cyberspace Authority recently added 11 generative AI services to its completed registration list, bringing the city's cumulative total to 211. This should be read as a signal about governance and commercialization, not as a measure of revenue, quality, or user traction. It indicates that in one of China's major technology hubs, launching a generative AI service is now tied to a visible and structured administrative process. There is still a lot the source does not reveal. It does not specify which services were added, what detailed review standards were applied, or how Shanghai compares with other cities pursuing similar systems. But the direction is clear enough. AI deployment in China is increasingly moving through formal regulatory channels, and that formalization is itself becoming part of the competitive landscape. In other words, technical capability alone is no longer the whole story. Regulatory throughput also matters. The final bottleneck sits outside China, but it can still shape Asian companies directly. According to the source material, key transparency obligations and enforcement mechanisms under the EU AI Act came into force on August 26, pushing AI governance closer to a board-level responsibility rather than a purely technical issue. For Asian firms that build AI products, incorporate third-party models, export software, or serve customers exposed to the EU market, that likely means heavier expectations around documentation, disclosure, and internal oversight. The source here is an op-ed rather than a legal breakdown, so the point should remain high level. Even so, the strategic implication is hard to ignore. Governance quality is becoming part of market access. Companies that can demonstrate disciplined oversight may be better positioned to operate across borders than those that treat regulation as an afterthought. Put together, these 6 developments form a single chain. xLight shows that the frontier of AI chips still depends on the physics and productivity of lithography. AMEC shows the effort to broaden domestic control over semiconductor equipment. AXT and Lumentum show material security being reinforced through long-term capital commitments. Alibaba shows model architecture being used as a response to hardware limits. Shanghai shows commercialization becoming more dependent on regulatory process. And the EU AI Act shows governance standards extending into cross-border competition. These are not coordinated moves, and they should not be forced into a single grand strategy. But they do point in the same direction. Asia's AI competition is shifting away from headline claims and toward execution infrastructure that is harder to see, slower to build, and much harder to fake. For investors, that argues for discipline over excitement. In semiconductor equipment, the real tests remain validation, qualification, and adoption. In materials, the key signal is whether prepaid, long-term supply structures spread more widely. In AI models, the question is whether efficiency-focused systems produce clearer technical disclosure and real enterprise demand. In governance, the focus should be on how registration systems evolve and how compliance obligations affect software and platform vendors selling across borders. The next winners may not be the companies making the loudest AI announcements, but the ones that control, secure, or navigate the bottlenecks everyone else depends on.